All right, so we are on 216, theoretical probability. Theoretical probability is simply what are the odds of something happening in theory. So not always a for sure thing, but in theory, based on the data, what are the odds? So most common theoretical probability is probably the lottery. So this first one seems pretty daunting. It's not too bad once you break it down. I think it's probably one of the harder ones in this section, but we can do it. So a state lottery runs a weekly game in which players must pick 5 numbers from numbers 1 through 45. A player can win by matching at least 2 out of the 5 numbers that are drawn for the week. So hopefully you've seen the lottery being played. If you're not 18, you might not have played the lottery. If you're over 18, maybe you have played. There are a lot of ways to match only 2 numbers and fewer ways to match more numbers, making the outcomes much less likely. So the chances of you matching all 5 numbers, pretty rare. The chances of you winning 2 out of the 5 numbers, a little bit easier. So the table shows us the probability of these different outcomes for a particular drawing and how much you would win in each case. So if you match 2 out of the 5 numbers, you win $1, because the chances of you doing that is like 1 out of every 12 times you play, you'll match 2 out of the 5 numbers. Okay, versus matching all 5 numbers, it's 1 in almost a million chance. So you've got a lot higher winnings there. You got $10,000. So find and interpret the probability of winning at least $200 by playing this lotto game one time. So to win $200, you need to match 4 out of 5 numbers. The chances of doing that are 1 out of 6,109 times. So also, if I looked at just like the decimal number of that probability, I rounded. You could round it more simplistically. You've got 2 out of 10,000 times, so 1 out of every 5,000, 6,000 games you play. Okay, what's the probability that you win something, whether it's $1 or $10,000? And what's the probability that you'll win nothing? So in order to do that, I'm actually just going to add all of those decimals together. I'm adding all the fractions, which I'm adding all the decimals together for that. So I listed those out. When I add them together, I get around 0.09, which means that I have a 9% chance of winning, which means that I have a 91% chance of not winning. And that's winning anything. You've got a 9% chance of winning something. Most likely you'll probably just win $1. So anyway, part C. If you play this game once a week for an entire year and you win something 3 times, are you doing better or worse than expected? Okay, remember, we have a 9% chance of winning. That's our expected chances. Okay, we're saying we won 3 weeks out of the entire year, which is 52 weeks. So I turn that into a percent, and that's about a 5.8%. 5.8% of the time I won something. So you are actually doing worse because you're expected to win 9% of the time. You only won 6% of the time. Okay, not doing so well. All right, moving on. Theoretical probability. Here is the definition. I'm not going to read through it. It looks kind of scary if you ask me. Here we go. We've got the number, an event that is a probability of 0% is known as an impossible event, while a probability of 100% denotes a certain event. Okay, to find theoretical probability of an event, with equal likely outcomes, find the ratio number of favorable outcomes to the number of possible outcomes. Okay, so moving on to number 2. Suppose you have a bag of 5 blue marbles, 14 red marbles, and 9 green marbles. You pick One out of the bag. What is the theoretical probability of picking a blue marble? Okay. Favorable outcomes out of possible outcomes. Okay. Basically, part out of a whole is what they're saying. Just in fancier words, because I'm sure you're sick of hearing part out of a whole. That's really what you're trying to find. Okay, so 5 out of 28. There are 5 blue marbles out of a total 28 marbles. 5 plus 14 plus 9, 28. Okay. What is the theoretical probability of picking a green marble? Again, what do they say? Favorable outcome out of possible outcome. Part out of a whole. There's 9 green marbles out of a total 28 marbles. Let's see. Got some more examples. Number 3, how many different outcomes are possible when 3 fair coins are flipped? Okay, 3 fair coins, really just a coin. Are they likely equal? So let's see. Let's list out the different outcomes when you flip a coin 3 different times. Okay, so first, I could get all heads. You flip it, head, head, head. I could flip it, head, head, and then I get a tail. I could flip it, heads, tail, heads, tails, heads, tail, or tails, heads, heads, tails, tails, head, tail, head, tail, head, tail, tail. Okay, and tails, tails, tails. Okay, so that's 8 different outcomes, all equally possible. All right, so we listed all of them out just like they did with these rolling 2 fair dice. What are the probable outcomes? Okay, listed all of flipping a coin. It's pretty daunting, I know. There's 8 total possible. Okay, what is the probability of flipping 3 fair coins and getting all heads? Okay, so let's start with that one. They're asking a lot of questions. We're just going to start with the first one. Okay, so getting all heads. Well, that was 1 chance out of the total 8. So all heads is 1 out of 8. What is the probability of not getting all heads? Well, if there's 1 in 8 chance of getting a heads, then that means there are 7 out of 8 chances of not getting all heads. And then the last one, what is the probability of getting at least 1 of each heads and tails? Okay, so you get heads at least once and tails at least once. Okay, that's 1, 2, 3, 4, 5, 6. Okay, hopefully you followed along with my counting. At least 1 of each. That's 6 out of 8 times. We can reduce that to 3 out of 4. Okay. Part C, if you flip 3 fair coins 10 times and get all heads only once, how does this experimental probability compare to the theoretical probability? Okay, so the experimental probability is you actually doing it, to the theoretical probability of this is probably what's going to happen in theory based on the data. Okay, so the experimental, you get heads 1 time out of the 10 times that you flip the coin. Okay, that's what we did. That's what actually happened. 1 head or 1 all heads out of the 10 total times that you flipped. Versus the theoretical probability that we said it would happen 1 out of every 8 times. Okay, so let's compare those 2 fractions. I think comparing them as percents is easier than comparing them as fractions. So I converted them to 10% versus the 12.5%. It actually happened 10% of the time out of the theoretical 12.5% expected. So it happened less than what we expected. Okay. Number 4, is this our last one? Yes, number 4 is our last one that we'll do together. The last problem makes the important point that experimental and theoretical probability for the same event can be and often are different. The 10% versus the 12%. The experimental probability tells us what percent of the time something actually happened. So we actually did it. Whereas theoretical probability tells us what percent of the time we expect an event to happen. Usually, the more times an experiment is conducted, the closer to the experimental probability gets to the theoretical probability. So suppose there is a raffle with numbered tickets. One ticket is randomly drawn from a hat. Your ticket is number 121. Find the following probabilities of winning. State your answer as a fraction, a decimal, and as a percent. Okay, so there's 200 tickets. What's your chance of winning? Well, you have one ticket out of the 200 tickets. So write it as a percent, or write it as a decimal, write it as a percent. Okay, you've got a 0.5% chance of winning. Okay, what if there's 400 tickets? Again, you still have one ticket out of 400 people. Okay, decimal, percent, you've got a 0.25% chance of winning. And what if there's 1,000 tickets sold? Again, you still have one ticket. That's 1 out of 1,000 times. As a decimal, as a percent, you've got a 0.1% chance of winning. What happens to your chances of winning as the number of tickets sold increases? Okay, so what happened to our chances of winning? We started at a 0.5% chance of winning, so 0.5%, and then we got down to a 0.1%, so 0.1%. So as more tickets were sold, your chance of winning decreases because you are just one out of many tickets, and then many more tickets, and then many more tickets. Okay, so chances of winning decreases. If 150 tickets were sold at a raffle, how many tickets would you need to buy in order to have a 10% chance of winning? Okay, so you want a 10% chance of winning. How many tickets do you need to have out of the 150? So X represents the number of tickets you need out of the total 150. Okay, so then we solve for X. I'm going to multiply both sides by 150. I need to turn that percent into a decimal as well. But once I solve, you need to actually buy 15 tickets in order to have a 10% chance of winning. Okay, then I actually skipped question number 5. I didn't like it too much. So go ahead and start your homework problems.